Hello and welcome back to our course. So in the last session we finished our vectorized NumPy code and we are now able to simulate the purchase of a certain amount of stickers many times. And now in this session we want to automate this process by writing a function. So later when we want to variate the parameters and repeat the process many times, it is much simpler and we also increase the readability of our code if we just have to call a function and just variate the parameters within the function. So first of all, let's import NumPy as always. Then we define the sticker album NP function, so for NumPy. And our parameters are the album capacity. So we set the default argument to 600. We have purchase stickers 800 and we have simulations 1000 and we set the seed to 123. And yeah, this is actually the code that we know from our earlier sessions. So we have our random seed. Then we simulate the purchase of random stickers where we have 1000 times 800 stickers. So we multiply the amount of sims with purchase stickers and reshape it into a matrix with, in this example, 1000 rows and 800 columns. And then we sort our matrix row-wise. So we can apply NP sort or the method sort. So that's we can do both here. And then for each simulation or for each row, we calculate the amount of unique stickers. And finally, we calculate the mean of our results. So here we get an array with, in this example, 1000 results for 1000 simulations. And then we calculate the mean of our simulations. And then our function returns the mean. So let's run our function. Let's define our function. And let's check if this works. So we set purchase stickers to 1491. So from part 1 we know actually that 1491 stickers is the amount we need that we get on average 550 unique stickers. So let's check it out if it also works with NumPy code. And there we are. So we get on average 550.17 unique stickers. So far we assumed that our vectorized NumPy code is much faster than our code with the Python standard library tools. And actually now it's time to prove that our assumption is correct, and therefore we copy our basic NumPy code that we already developed in part 1 here. So that's the code. So also here we set a seed and then we take 1000 simulations and 1000 times we create an album. And for each album we create 800 random stickers and we check if each sticker is already in the album. If it's already in the album, we do nothing. And if it's not in the album, we stick it into the album. And then in the end, for each album, we calculate the length of unique stickers, so the amount of unique stickers. And then we append the length of each album into our results list. And finally, we calculate the mean over all results and return the mean. So that's basically exactly the same function in terms of functionality than our NumPy code, our NumPy function. So before we measure the time each function requires with the time_magic function, we first of all calculate actually the expected unique values for purchase stickers equal 1491 and 1000 simulations. So we would expect for each case actually, of course, 550 unique stickers. First of all, we import random and we run the function. And then we calculate for the Python standard library function the unique stickers. You can see here it takes a little while. So the Python standard library function returns us an expected value of 550.01. And let's do the same with our NumPy function. So simulations is also 1000 and purchase stickers 1491. Yeah, there's a very small difference because, as I said before, even if you take the same seed for the NumPy and the Python standard libraries, so they do not return the same random numbers. So that's no surprise that there's a small difference here. And now let's measure the time each function needs. So now for the Python standard library function, we got 6.74 seconds. And now let's measure the time for our NumPy function. We get 84.6 milliseconds, so there's actually a difference, or the NumPy code is about 80 times faster, so that's quite a lot actually. So I think we can do many more things with our NumPy code, because we are much faster. Alright, so let's fine-tune our NumPy function. And we can set simulations to maybe 5000 because we are so fast. And so far our function returned the mean of all simulations, and so to say the average that we can expect. And now I want to move to a more probabilistic approach, and I want to return the low percentile, the median and the high percentile of our results array. And therefore I calculate here the median, so NP median of our results, and I round it to 1 digit. And also I calculate the low percentile and the high percentile. And both the low percentile and high percentile I also introduce as arguments or parameters to the function, because I will also be able to change the percentiles. To say, instead of having a low percentile of 5, I could also switch to, let's say, 10 or 25. So now let's define and run our function. And then we can call our function with, let's say, 10,000 simulations, 1,491 purchase stickers, a low percentile of 5 and a high percentile of 95. And let's see what we get. So actually we get a tuple of results. So here the first result is actually the low percentile, the middle result is the median, and the third result is in the high percentile. And now the intuition is to say that, okay, if we purchase 1,491 stickers, it is 50% likely that at least we get 550 unique stickers. And also we can say that there's only a risk of 5% that in the end we result in getting less than 540 unique stickers. And there's at least a chance of 5% to get more than 560 stickers. And also in total we can say that in 90% of all cases we end up in the interval 540 till 560. So instead of having just the mean, the median and percentiles, gives me a better intuition how likely it is to end up with a certain result. And also now we can change to low percentile of 1 and high percentile of 99. There we can check where we will end up in 98% of all cases. So in 98% of all cases we end up between 536 and 564 unique stickers. And of course we can also check, let's say, low percentile 25 and high percentile 75. So that means in 50% of all cases we will end up in the interval 546 till 554. Alright, so now we have developed all tools to proceed with more advanced problems, and in the next session we will introduce the possibility that we can exchange and trade duplicates with others. So I hope to see you in the next session.